A second example that I'd like to do involves finding the slope of the tangent line, or instantaneous rate of change, for the function f of x is equal to x squared, again at the arbitrary point x0. So as before, we're thinking first of all of the average rate of change on the interval from x0 to x0 plus h, and then after we find the expression for the average rate of change, we'll take the limit again as h approaches 0, or as the right endpoint approaches the left endpoint. So we have first off x equals x0, and then the function value would be the square root of x0. All right. At the other end of the interval, we have x equals x0 plus h, and f of x is the square root of the quantity x0 plus h. Now notice the change in x, as has been, is going to be x0 plus h minus x0, which is just h, and the change in y will be the square root of the quantity x0 plus h minus the square root of x0. So the average rate of change will be the change in y, square root of the quantity x0 plus h minus the square root of x0, all divided by the change in x, which is h. So we have this expression as our average rate of change in square root of x over the interval from x0 to x0 plus h. Now, to find the instantaneous rate of change, or to find the slope of the tangent, we'll take the limit of this expression as as h goes to 0. Okay, now we need to remember here, all right, the formula. Most students remember this one, so I haven't put it ahead of time, but that a squared plus b squared is equal to the quantity a plus b times the quantity a minus b. Need to remember that, because what I want to do to simplify this, I want to get rid of these radicals. And so notice that this is the difference here. It's like the a minus b. If I multiply by the sum of these, then the radicals go away. And again, most students remember that, but of course I'll have to multiply by the sum of that expression over itself, because if I multiply by 1, nothing changes. And this expression, the square root of x0 plus h plus the square root of x0 over itself, is of course 1. All right, now as I multiply this out, what am I going to get? In the numerator, I'm going to get just the x0 plus h, because I'll get the first term squared. By the way, this is called, sometimes when we just change the sign on the second term, it's called the conjugate. All right, and I'll get the first one squared, like the a squared here, and that would just be x0 plus h, minus the second one squared, which will be the square root of x0 squared. That'll be x0. And if you multiply that out using the FOIL method, all right, you'll see that that happens. In the denominator, I'll get h times, I'm not going to multiply it out, and you'll see why in a second, the square root of x0 plus h plus the square root of x0. Oh, I forgot. Remember, we're taking the limit of this. So the limit as h approaches 0. Now, of course, in the numerator, we have x0 plus h minus x0. Okay, so that's just h. And so this becomes the limit as h approaches 0 of h over h times the quantity square root of x0 plus h plus the square root of x0. The h's cancel, leaving a 1 in the numerator, and we're left now with the limit as h approaches 0 of 1 over the square root of x0 plus h plus the square root of x0. Notice now as h goes to 0, all right, provided that x0 is not 0. Now that in the last example that couldn't happen, but in this example we could have x0 being 0. But we'll see that there's another problem in just a minute. And provided x0 is not 0, all right, this becomes 1 over the square root of x0 plus 0 plus the square root of x0. All right, or 1 over 2 times the square root of x0. And now you see we have a formula for for finding the instantaneous rate of change for the square root of x. Okay, let's take a look at this example. Okay, oops, I have somehow the wrong one here. There it is. Okay, here's the square root of x, and if I look at this at 1, all right, as I take the, let me look at the tangent line, so here's 1 and 16, so in this case the h would have been 15, 1 is x0, 16 is x0 plus h, so h must be 15. So I have the slope of the line between the point 1, 1 and 16, 4. And now if I let h go to 0, all right, you see when it gets to 0, notice, all right, that I have here, I forgot to show the information, but I have here the slope is 1/2. The slope is 1/2. Let's see, does that fit with our prediction here? Well, if x0 is equal to 1, that implies that the slope of our tangent line is equal to 1 over 2 times the square root of 1, which is 1/2. And so that does work. Now here's the thing, but again, if I let x0 be say 4, I'll try to get it to 4 without too much trouble. All right, at 4, oops, I've gone past 4 just a little bit. But I may not be able to get it. Oh, there we go. All right, notice at 4, all right, the slope is 1/4. All right, it's not as steep. All right, but if at 4, all right, if x0 is 4, then we'd have 1 over 2 times the square root of 4, 1 over 2 times 2, which is 1/4. Okay. Now here's the problem, here's one of the issues with x0 being 0. Notice if x0 is being 0, notice what's happening to that tangent line. Oh, and notice that, by the way, Mathematica gives me a little bit of an error here. All right, if I do that, but the tangent line becomes vertical. Now, when the tangent line becomes vertical, all right, it doesn't have a slope. The slope value is undefined. So this formula could not possibly give us a value, or shouldn't give us a value anyway. It should be undefined. We could think of the slope as being infinite. Okay, a change in x would produce an infinite change in y. I guess we could think of it that way. Maybe that's not exactly proper. Okay,